So hello everyone, welcome back to this class. So we have covered Bode plot and root locus. Now today class we will see the Nichols chart and Nyquist plot, right? So first we will see the Nichols chart. You will see so the command is Nicols in bracket G. So this is a command, very simple, right? Like Bode, you have a Bode G, G is the transfer function, right? So now first I will take the transfer function. When you hit the run button, you will get the transfer function what? 1 upon s plus 1, right? So that means one pole at a -1 location on a left half plane. So in Bode plot generally you can see here, you will see the gain and phase with respect to the frequency. So in Nichols chart what it will happen, you will remove the frequency and you will plot between gain and phase. So you will not be able to see the frequency, but each frequency you can actually see the gain and phase on a one plot. So how to draw the Bode plot, that already explained to you. So you take the gain and phase and you can plot here, and you can see that key open loop gain and open loop phase here. Okay. Take your cursor along this line, you will see that key your frequencies keep on increasing, right? Your frequencies keep on increasing. So here, from here to here, you can see the increase in frequency, but in a Bode plot you can see when you increase the frequency how the gain is dropping and how the phase is dropping. For example, let's say here you have a phase of almost 0, and now here you have a phase with respect to the frequency, your phase is more negative, right? So similarly you can see here in Nichols chart, when you come along this line, you will see the increase in frequency. Okay, so you can each and frequencies, you can see open loop gain and open loop phase actually. So it is a very simple, you remove the frequency from the Bode plot and you plot the gain versus phase plot here. Okay, we can take the example of 1 by s as an integral. So in Bode plot we have seen that when you plot this, you will see the phase is -90 and gain is dropping by 20 dB per decay. We have already seen. And now in Nichols chart you can also see this see here for all frequency your phase remains the 90 degree. So that is why you see the vertical line here. Okay, so it is easy to understand the gain and phase on a one plot using the Nichols plot, and it is plotted in the Cartesian coordinate, so very simple to read. Okay, so this is the another way of seeing the Bode plot actually, very simple. And let's say if you take the example of s only, like we have seen in the Bode plot case. So transfer function s, okay, that means what, you are just taking the derivative. So we will see, we have seen that the phase will remain the 90 degree and your gain will increase. Already we have seen in the Bode plot class. In both theory, in flight control system design and Simulink in this course. Okay, so you can see for a all frequency the phase is plus 90 only. So plus 90 for transfer function s case and minus 90 for the transfer function 1 by s case for a all frequency you can see. So this is the purpose of the Nichols plot. Okay, similarly you can draw for a spring mass system also. So you can take m equal to 1, c equal to 1, k equal to 1, and you can actually see the Nichols plot at each and single frequency. Okay, and here if you click the all stability margin, you will be able to get that what sort of phase margin you are having. Okay, whether your closed system is stable or not. So this is the importance of the Nichols chart. We will see the Nyquist plot. Okay, So in Nyquist plot, what generally you do? In any root you can represent on a complex number, like 1 minus 1 plus 2y you can represent on a complex plane. Okay, right? When you put s equal to j omega, for example, let's say you have a transfer function s plus 1 divided by s plus 2, right? When you put s equal to j omega, you will get j omega plus 1 into j omega plus 2. So you will multiply by the conjugate and divide by the conjugate, you will get new complex number, right? So you will plot under the new complex plane. So let's say this, the original one, previous one complex plane was S plane, and you can say this is a S dash plane. For example, you have to locate this as a one complex plane, right? So you can consider as a S plane, and now this, if you do the process, you will get the another complex number you can represent on the another plane. So every time you will do, for each frequency you will do, right? So you will get the different complex number. So in order to do this, we generally use the Nyquist plot in order to see how at each frequency the system is behaving. So actually it is used for a non-minimum phase. We have already seen that key where the Bode plot will fail, the Nyquist will take care, right? So what is the first step in plotting Nyquist things, right? First you put s equal to j omega, okay, and then you will calculate by putting omega equal to 0 and omega equal to minus infinity, plus infinity, and then at the third step you will equate to real part 0 and imaginary part 0, okay, and final step you will plot. For example, have you remember we have plotted the spring mass system Nyquist plot, and it was coming like this, right? So what is this point? -1, right? You should never hit to this -1 point, right? If you are not hitting this point, that means you are stable, right? And why from 0 to infinity? See, first you have to calculate by putting omega equal to 0 and then omega equal to infinity, because when you put omega equal to minus infinity, it is a mirror image, right? So you draw for only one part and take a mirror image, other part will be automatically drawn. So that is why you take 0 to infinity, not from minus infinity to plus infinity. And we have already seen that when the increment is clockwise, the system is stable. So this is which direction? Clockwise. And this is what the coordinate? 1 comma 0, right? And this is what? 0 comma 1, right? This is 0 comma 1. So all this point you can find out using the procedure, right? We have already seen the Nyquist class. Now, so it is coming here and going to the origin, right? So let's say if I will change the damping, let's say -1. So you will see, if I will change the damping -1, what I am doing? I am making the system unstable, right? So let's see. So what is the direction of this now increment? Anti-clockwise, right? So you can see this is a unstable because damping is negative. So if you understand the Nyquist concept, how to plot the same, then actually you can use the MATLAB as a tool and you can actually plot. So in theory we have seen, put s equal to j omega, rearrange in a proper complex number, and then put equal to omega equal to 0, calculate, put equal to omega equal to infinity, calculate, and then put real part 0, calculate where it is crossing to the imaginary axis, put imaginary part 0, you will see how it is crossing on the real axis and just draw. And we have already seen, by using that approach, you will not be able to claim whether my circle is, whether my graph is like this or like this. roughly you will able to find out the shape, but you will not be able to how big, how small it is. But using MATLAB, actually we can actually accurate to see these things. So see how important is a MATLAB tool in order to see. Now you can see any transfer function. You just name it. I will plot here. Okay, but first thing you should understand the theory behind it. Now we will see all four together, right? So let's say we have taken transfer function what? Just a derivative, right? Just a derivative I have taken. So you can see in a Bode plot you will see the gain will keep increasing, phase will be plus 90. Okay, now you will see the root locus. So your root locus is what? You have only one zeros, right, at a origin. You don't have any pole, right? So that is why you don't see any cross mark. You just have a one pole at a origin. So simple, root locus is also simple. Now in a Nichols chart you will see already we have seen plus phase is plus 90 for all frequency. And what about this Nyquist? So it is not, it is actually at a origin, right? It is not crossing imaginary axis and not crossing the real axis. Okay, but as long as you will increase the frequency, what you will go? You are going towards the infinite, right? So it will never come to near -1, right? You will write transfer function S. What you will do? You will put j omega, right? First step. So what you will write? J omega in step 1. And in next step what you will do? You will put omega to go to 0. You will get 0. You will get omega to infinity. You will get infinity. That is why it is going to the infinity. And it will never cross the imaginary axis and never cross the real axis. So that is why when you see this type of jump line, vertical line, you should don't confuse. If theory part is clear, no problem at all. Now you have a feel for why I am putting omega equal to infinity and why it is going. It is the second step, right? First step is what? You put j equal to s equal to j omega, then rearrange in a complex number. Next step, put omega equal to 0, calculate, and put omega equal to infinity and calculate. And in a second step itself, I am able to know that why this line is coming. Why this line is coming. Okay. And in third step, what you will do? You will check how my Nyquist is crossing on the real axis and imaginary axis. So that is why if you want to check how it is crossing to the real axis, you will put the imaginary part 0, like this. So like this case. Like this, whether it is crossing on the imaginary axis and where it is crossing on the real axis. So are you people having any doubt? No, right? Okay, so when you see this type of graph, you do not confuse with this key why it is coming. Okay, so this is all about the Nyquist plot. So if you have any doubt, you may ask me. So now the Bode plot is clear, root locus is clear, Nichols chart is clear, Nyquist plot is clear, theory already explained to you. In MATLAB Simulink I have shown to you what is the command we are using, that also you can note down. So the command is very simple. I will try to explain the code here also. See, first what I have written, I have clear CLC close all standard one. Now you use the numerator and denominator coefficient. You write the transfer function g equal to tf G num D den, okay. And now whatever you want to plot, as in figure 1 I want Bode, figure 2 I want Nyquist, figure 3 I want Nichols, and figure 4 I want root locus. You just give the command Bode, Nyquist, Nichols, root locus, R locus with the transfer function G. Okay, we'll meet in the next class. Thank you.